Video will take a look at sound waves. Specifically, it'll primarily focus on sound waves in gases or air. In the last video, we said that a sound wave is effectively a traveling variation in pressure. So we've got regions of high pressure and low pressure. Those regions of high pressure and low pressure travel from their source to maybe our eardrum. And cause the eardrum to oscillate or to move. And then that motion is transmitted to the auditory nerve, and then that gets translated to sound in our brain. All right, so a sound wave is effectively a traveling pressure variation. Here we've got some speeds of sound in various media, in gases, liquids, and solids. At least we would have them if my head weren't in the way. So a couple ones that I want to pick out. Let's see, we've got the speed of sound in air. Let's see, at freezing temperatures, 331 meters per second. At 20 degrees Celsius, it's 343 meters per second. Let's see, that's, what is that? That's about 68 degrees Fahrenheit. Let's see, if we look at maybe the speed of sound in helium. The speed of sound in helium is much faster than the speed of sound in air. That's part of the reason why if you inhale from a helium balloon and then speak, your voice sounds all high-pitched. Moving on to liquids, we see that the speed of sound in liquids is much faster. If we look at, for instance, water, then it's around 1,500 meters per second. And then if we were, if my head weren't in the way, we would see that in solids, it's faster still, maybe around 5,000 meters per second or so. This is largely down to the density of the material and the stiffness of the material. All right. We can quantify the speed of sound with at least, in gases with the equation that's on the screen there. This equation uses the ideal gas model, the idea that basically we're going to have very little interaction, any kind of bonding interaction between gas molecules as maybe they bounce off of each other. Anyway, it uses that model to kind of describe the speed of sound in a gas. This says that the speed of sound in a gas is equal to a gamma factor times Boltzmann's constant times the temperature in Kelvin divided by the mass of one gas molecule. That gamma value, which looks kind of like a Y, but that's the Greek letter gamma, is 5/3 if the gas is monatomic, and it's 7/5 if the gas is diatomic. So that's, again, my head's in the way of the word, but the missing word there is diatomic. So a diatomic gas molecule would be, examples of those would be something like nitrogen or oxygen or let's see, hydrogen, something like that, where the molecule is formed from two atoms. A monatomic gas molecule would be something like helium or argon or neon. Any of those noble gases would be monatomic. All right, so there's our equation. Let's take and do something with that. Okay. We are interested in the speed of sound in air. Let's see, at a temperature of 23 degrees Celsius. So at 20 degrees Celsius, that's about 68 Fahrenheit. At 23 degrees Celsius, a little bit warmer, mid 70s, maybe something like that. And we would like to be able to calculate that value. It says here that we can treat air as if it's diatomic, and it has a molecular mass of 28.9 atomic mass units. Okay, that's great. If we think about that equation had, let's see, the mass of an individual gas molecule in it. Our SI unit for mass is the kilogram. So we definitely need to do something with this value here. 28.9 atomic mass units. there are 1.66 times 10 to the negative 27 kilograms per 1 atomic mass unit. And so that's just a conversion factor that we would need to look up. And when we do the math there, we get that the mass of an individual gas molecule, an average gas molecule in air, is 4.8 times 10 to the negative 26 kilograms. So that's the value that we'll put into that equation. Let me erase here what I've got on the screen. There we go. It's probably an erase all button somewhere in here in PowerPoint, but I'll just do what I did. All right, so if we now pull out our equation, gamma KT over M, we can go ahead and pop in the values. For diatomic gas, gamma is 7/5. The value for K is 1.38 times 10 to the negative 23rd joules per Kelvin. I'm going to take advantage of that erasure that wasn't complete. That's negative 23, and just leave it there. And then it says 23 degrees Celsius. We need that in Kelvin, so we would need to add 273 to that Celsius temperature. That will give us 296 Kelvin then. And then I'm dividing all this by the mass of an individual gas molecule. That's 4.8 times 10 to the negative 26 kilograms. All right, and when I complete that math, I should get a value of 345 meters per second for the speed of sound at this increased temperature. So 345 meters per second. If we go back and we look at that list of values that I gave us, we should see that matches up pretty well with that value in the table of the speed of sound the speed of a sound in air at a temperature of 20 degrees Celsius. So this is pretty good matching with our result, or with the table that we had from earlier. All right. So this conceptual example says that we can tell how far lightning is if once we see the flash of lightning, we count off the number of seconds that pass until we hear the thunder. All right. So why does this rule work? Well, so the sound, the lightning flash and the sound both have the same source. That is the lightning. The lightning that occurs some distance away. If we take a look at the relationship between miles and meters, every 1 mile is 1.6 times 10 to the 3 meters. Now, if we divide 1.6 times 10 to the 3 meters by the speed of sound, the speed of sound at 0 degrees Celsius is 330 meters per second. We get the result that it takes 4.8 seconds for sound to travel a distance of 1 mile if we're at 0 degrees Celsius. So it takes approximately 5 seconds to travel 1 mile. And then as far as how quickly light travels at 3 times 10 to the 8th meters per second. So for all intents and purposes, it's nearly instantaneous across a distance of 1 mile for light to travel from the source to our eyes. We're talking about just bare fractions of a second. So this is why this rule works. It takes about 5 seconds for sound to travel 1 mile. That's it for this one.